Assalamu alaikum and welcome to second video of this week's lecture. Previously we discussed about the continuous data modality with unsupervised learning, and we discussed about the dimensionality reduction and some of the techniques regarding or at least we discussed one of the techniques, which was principal component analysis. Now we will dive into the discrete characteristics of the data while using unsupervised learning, which falls into the category of clustering. So clustering is a kind of a grouping with grouping the data with similar characteristics or with the points who are very close to each other in the neighborhood. So grouping those points together is a kind of a technique which falls under the category of clustering. So in this case, if you can just cluster all these basically states, like in the United States, if you want to cluster these states with respect to the population size, then this would be one similar result where you can see that Olympia and Rio Grande, Houston and St. Croix, these are actually similar in terms of population. So these are the clustering based on the similar population. Similarly, Bitterroot and Ojove, and this is Missouri, Great Smoky, Tombigby, Dallas. So these are basically clustered with respect to the similar populations. Now, in terms of computer vision, this is one of the example where we break up the image into meaningful or perceptually similar regions. And if we want to look at other examples for clustering, then let's say this is uh, the original image. We consider the patch of size 50 by 50 and we apply it. So we get this result while using Felsen's Wolf and Huttenlocher method. So you can see that it's a kind of a quite over segmentation, whereas if you apply superpixel segmentation, you get this kind of result. We have already discussed the types of segmentation and the methods of segmentation. So we will focus on the clustering technique itself rather than the result we get through the segmentation. Okay. So basically you can uh, like use my method, which is available on GitHub. So you can just try to replicate these results for segmentation. So the GitHub code actually is well commented, and you can use that on your own images, on set of images, to segment the image using ActiveSnakes, random walk, simple linear iterative clustering, Fezzel swap, and Felsen's Wolf plus senior simple linear iterative clustering. So we can just categorize different type of segmentation. Like if we want to over segment anything, like we want to segment very small clusters together, then it is also referred to as over segmentation. And if we want to just group like many pixels which are similar and we want just 2 or 3 clusters from whole image, then it would be a kind of a under segmentation. And there are also hierarchical segmentations which can go from over segmentation to under segmentation. So clustering is a kind of a grouping similar points and representing them with a single token, and the key challenges which are involved is what makes 2 points images patches similar. How would you find similar patches? How would you find similar points? And the second thing is how we compute an overall grouping from pairwise similarity. So what is the criteria of computing those groupings? And the next questions are, why do we cluster? So it can be for summarization, like we want to summarize the data as we did through the map. So looking at large amounts of data, batch-based compression or denoising is one of the application which use summarizing data and representing a large continuous vector with the cluster numbers. Also, it can be used for feature vectors, extraction of feature vectors such as histograms of textures, colors, shift vectors. It can also be used for segmentation, which we will continuously discuss throughout this video, that how we can use these clustering techniques for segmentation and prediction. Like if the images fall under the same cluster, then it may have the same levels. So how do we cluster? One method is k-means clustering, which iteratively reassigns points to the nearest cluster center. We'll look into the details, not with the mathematical point of view, but with the logical point of view, that how k-means works. And then agglomerative clustering, which is like starting with each point as its own cluster and iteratively merging the closest clusters and forming a big cluster at the end. And then mean shift clustering, which estimate modes of probability distribution function. We'll also look briefly at spectral clustering, which is splitting the node in a graph based on assigned links with similar weights. So let's start with k-means clustering. So what do we do in k-means is we randomly select k centers and we assign each point to nearest center, and we then compute new center mean for each cluster. And I think we have already discussed a little bit of k-means in image segmentation algorithm. So this is one of the animations for k-means. Now here this is a simple pseudocode for it, like initializing the cluster centers. So once we initialize it, we assign each point to the closest center by using this formula. Here k is actually number of clusters, n is the number of data points, c is the cluster center with index I, x is the data point with index j, and the delta here is the indicator variable which says whether x is assigned to c or not. So in the next step, we want to update the cluster centers as the mean of the points, and we would repeat the steps 2 and 3 until the convergence. So the k-means convergence starts with like this. We like initiate the cluster centers, and then we, as stated here, we assign each point to the closest center and update the cluster centers accordingly. So here we initiate it, we find the closest points, we update it, find the closest points, update it, find the closest points, update it, and this is how we come to the convergence of k-means. Now let's think about that how like what is good about k-means, why do we use k-means at all, and what are the disadvantages of k-means, and where could we specifically apply k-means. I will share the answers at the end of this video, so just look for it. So k-means, there are many design choices for k-means, like what would be the initialization, how to initialize the randomly like k points as the initial cluster centers, and we can do it randomly, of course, or we can just greedily choose k points to minimize residuals. We can consider many distance measures. Probably most of the studies use Euclidean distances, but we can use Chebyshev, we can use Manhattan distance, we can use many other distances which are available in most of the libraries. And then we can also opt for optimization, which converges to a local minimum, and it may want to perform multiple starts if it stuck a certain plateau. So this is one of the examples where I gave each pixel the mean intensity or mean color of its cluster. This is basically just vector quantizing the image intensities colors. Notice that there is no requirement that clusters be spatially localized, and they are not. So basically this type of clustering is also used for image compression, and it has been very popular for compressing the images, like reducing the size of the image while keeping the quality same. Now, how to choose the number of clusters? We can use a validation set. By saying validation set, I mean that we can try a different number of clusters and look at the performance, that how it is performing. If it is performing better, just update the number of clusters. Otherwise, just stick with the previous number of clusters you have tried to decide. And when building dictionaries, more clusters typically work better. So there is another variant of k-means clustering, which is k-means plus plus, and k-means plus plus is just an initialization procedure for k-means. So in k-means plus plus, you pick the initial centroids using an algorithm that tries to initialize centroids that are far apart from each other. You pick a point randomly, and that's your first centroid. Then you pick the next point based on a probability that depends on the distance to the first point. The further apart the point is, the more probable it is. Then when you have two centroids, you repeat the process. The probability of each point is based on its distance to the closest centroid to that point. This introduces an overhead in the initialization of the algorithm, but it reduces the probability of a bad initialization, leading to a bad clustering result. We will not go into further details, but if you want to know a way to choose number of clusters or how to evaluate clusters, then find the hidden slides in this presentation, which I am going to upload on Google Classroom. So this is a kind of a pseudocode which I have already explained, but it's a simple way of putting it. Like, choose one center uniformly at random from all data points. For each point x, compute the distance between x and the nearest center that has already been chosen. Choose one new data point at random as a new center using a weighted probability distribution where a point x is chosen with probability proportional to the square of the distance. Repeat steps 2 and 3 until k centers have been chosen. So for more demos, you can actually go through these links. They provide demos for k-means clustering. Let me show you some of them. So this is one of the demos which I already explained you, like assigning the states with equal population. So you can go through this link. Another demo can be found at this website, where you can just reinitialize different problems, and you can just drag out the circles at different points for the initialization, and then you can just use different methods for data generation, and you can just consider the points. Let's say if I use 400 points, and if you want to change the clusters, let's say just change the clusters to 6, and then iterate the algorithm, so you can see that the cluster centers are changing and the data points are actually assigned to different clusters. So another demo is here. So here you have to just select the value to start. Let's say we select this 5, and it will automatically try to assign means or the cluster centers. So it will try to update it accordingly. So these black dots represent the initial means, and these are the clusters, like cluster 0, cluster 1, and cluster 2, cluster 3, cluster 4, and these are the updated centroids. And it took almost 21 iterations to come up with these centroids. And let's get back to our presentation then. So the advantages of using k-means is that it finds the cluster centers that minimize conditional variance, which again represents the data good enough, and it is simple and fast and easy to implement. So there is no kind of complexity in implementing k-means. The disadvantage is, the main disadvantage you can say, is to choose k. So we do not actually know that how many cluster centers actually exist. So we have to choose we have to initialize the cluster centers, and it is very sensitive to the outliers, and it is prone to local minima, and all clusters have the same parameters, that is same distance measure, so it's not adaptive, and it can be slow. So each iteration is O2, K, and D for n dimensional points. and its usage is mostly for building visual dictionaries, or you can say extracting feature vectors. So this is one way to build the visual dictionaries. Let's say you can use it for 128 dimensional shift vectors, or you can just use the cluster centers as the dictionary words, or you can use them to match new features like for classification as well. So these are some of the examples of learned code words, and you can find more details in this publication by Civic et al. Now another method for using clustering is agglomerative clustering, where you say every point is its own cluster. So you find most similar pair of clusters, you merge it into a parent cluster, and then you repeat it. So whenever you repeat it, it becomes a single cluster at the end. So the agglomerative clustering is the most common type of hierarchical clustering used to group objects in clusters based on their similarity. It's also known as AGNES, agglomerative nesting. The algorithm starts by treating each object as a singleton cluster. Next pairs of clusters are successfully merged until all clusters have been merged into one big clusters containing all objects. The result is a tree-based representation of the objects named dendrogram. So how to define cluster similarity? You can use distance measures like means or medioids, or you can use average distance between those points, or you can use maximum distance or minimum distance. Now how many clusters? Again, it depends on the threshold you choose. So if the threshold is based on max number of clusters or based on distance between merges, then the clusters will be formed according with that particular criteria. You can find some of the demos for agglomerative clustering as well. So let me show you one of them. So this is a kind of a implementation of hierarchical clustering. So you can follow this example. And for the visualization, let's say I choose randomly. Just restart. I choose randomly. Okay. So if you choose k-means clustering here, you can add centroid. You can add more centroids, you can add more centroids, and then go. So this is a kind of a k-means clustering. If you want to update centroids, again reassign points, update centroids, reassign points, and this will go until and unless it converges. Now here is one of the examples of hierarchical clustering. So you can just select hierarchical, and this will show you that what are the clusters, what will be the linkage. So if you want to select the average, then just again use k-means hierarchical and see this points that where you actually are. So if you want to point out this, then it means that these 2 points form a particular cluster, these 2 points are grouped to form a particular cluster, these 3 points, as you go up higher, the number of points for forming a cluster will increase like this, and as you see, it selects all the clusters. Now agglomerative clustering is good because it is simple to implement and it has widespread applications. For agglomerative clustering, it have also adaptive shapes, so you can just stop in between, or you can just go to the maximum abstraction. And it also provides a hierarchy of clusters, so it is easy to understand the tree with respect to the clusters which have been formed. But it may have imbalanced clusters, as we have seen in previous example or the demo, and we still have to choose the number of clusters, or we have to threshold, and we need to use an ultrametric to get a meaningful hierarchy. So ultrametric is a kind of a stronger requirement than triangular inequality. So it is a kind of a distance between 2 points which should be at least as large as the distance of connecting those 2 points through any intermediate. Now one of the what widespread method which is used for segmentation is mean shift algorithm, which is a versatile technique for clustering based segmentation. Now mean shift falls under the category of clustering algorithm in contrast of unsupervised learning that assigns the data points to the clusters iteratively by shifting points towards the mode. Mode is the highest density of data points in the region in the context of the mean shift. As such, it is also known as mode seeking algorithm. Mean shift algorithm has applications in the field of image processing and computer vision. Unlike the popular k-means cluster algorithm, mean shift does not require specifying the number of clusters in advance. The number of clusters is determined by the algorithm with respect to the data. The downside to mean shift is that it is computationally very complex, so its complexity is O to n square. So the mean shift algorithm is actually based on attraction basin. So attraction basin is the region for which all trajectories lead to the same mode, and cluster is all data points in the attraction basin of a mode. So here are a set of points drawn from a distribution, and you can tell obviously that the idea is that there probably is a mode kind of here. Okay, so there is the maximum concentration. So great. The question is which points belong to which mode, and that's done very simply by, if you were to start your mean shift in each of these locations, like these ones, these are the locations where you start mean shift, which mode does it end up at? So alright, and that's illustrated in this figure. So here it is shown that the area of which all of the mean shifts get to this mode, the mode on the right, so it goes here. Likewise, everywhere over here they get to this mode, the mode on the left. So it clusters your feature space using these basins of attraction to the modes. So when we do this for segmenting a color image, what we have to do is we have to define some feature, which is color, gradients, textures. So maybe we are using just U and V, or U, V, X and Y if we want a color and a location. So we have to initialize the windows at every pixel, that is every possible color point in LUV space. Now, would you do everyone? No, you would take a sampling of them. So you do mean shift until it converges, and then you merge all the pixels, all those initial points, into a single cluster that all end up at the same peak. So let's look a little bit like this. So here L and U space, and this is L and V basically. Okay, so these are the actual pixel colors distributed, and if you run your mean shift clustering here and here, it's being done in this LU space. You will see all these points going up to this peak right there, and then there are peaks here, here and here. So there are total of 7 modes, like 1 2 3 4 5 6 and 7, and that means there are 7 basins of attraction, which means you would end up with 7 regions in the image. So let's see an example here. So here we have a set of particles, and they are just drawn from some density, and probably if I were to ask you where's the mode, you would probably say here somewhere. And the goal is for the system to find that on its own. So let's put down a region. Okay, it's called a region of interest. Now we are not going to talk about the size of that region just yet, or its shape. Most of the time it is considered to be a Gaussian. So we have this region, and we calculate, okay, of all of the points in that circle, where is the mean or the center of the mass. And we say, oh, it's not right in the middle, and that difference between them, and that difference between them, that's called the mean shift vector. So this is called the mean shift algorithm. And so what do you do with the mean shift vector? Well, you shift the mean and there it goes. And then you again shift the mean and you calculate the mean shift vector, and then again you shift it. And then again, let's try it again. So what did we do, or what it does? It selects the weighted mean from the new samples, calculate the mean shift vector and shift it. As the mean shift vector gets smaller, shift, and then finally we are in the right spot, right there. So we can use different density estimation algorithms to illustrate. Suppose we are given a data set of X points in one-dimensional space, sampled from some larger population, and that we have chosen a kernel K having bandwidth parameter H. Together, these data and kernel function returns the following kernel density estimator. For the full population's density function, the kernel function here is required to satisfy the following two conditions. The first is needed to ensure that our estimate is normalized. The second is associated with the symmetry of our space. Now here the second one is the Gaussian kernel. So for the mean shift segmentation, we compute the features for each pixel, like we can extract color, gradients, texture, and we set the kernel size for features kf and position ks. Initialize windows at individual pixel locations. Perform mean shift for each window until convergence. Merge windows that are within width of kf and ks. So these are some of the results for mean shift segmentation. So the clustering is based on LUV colors, location XY coordinates, and eliminating small clusters. So this is one of the examples. The probable solutions to the speedups, other tricks, and theoretical support are hinted in the next slide, which is hidden. So you can go through it by downloading the slides from Google Classroom. Now the advantages for mean shift algorithm is it is a good general practice segmentation algorithm. It is flexible in number and shape of regions, and it is robust to outliers. But we have to choose the kernel size in advance, and it is not suitable for higher dimensional features. So where we use it when we need over segmentation, we use it when we need multiple segmentations, we use it when we have to apply tracking, clustering, and filtering applications. Now one of the other examples is spectral clustering, where we group points based on graph structure and edge coasts. We capture the neighborness or local smoothness. So basically it is a technique with roots in graph theory, where the approach is used to identify communities of nodes in a graph based on the edges connecting them. The method is flexible and allows us to cluster non-graph data as well. So for explaining this, I am going to assume you have seen some form of algorithm class, and you may have heard there's something called a graph cut algorithm. We have already discussed it in my previous lecture video, specifically the image segmentation part 1 lecture. So it does exactly what you think. It cuts a graph. So here I have got a graph, and the idea was originally it had lots of connections in it, and when I am all done, I have decided to break this graph on those 4 links to create 2 graphs. A, and let's suppose I name it A and B, and they are totally disconnected. So those would be 2 segmented inner image, and the idea is that the cost of a cut is quite simply just the cost of all segments that you broke. So that's what this thing shows you here. This one. And a graph cut would give you a segmentation of the image. So the question becomes, what is a good graph cut and how do you find one? So there are algorithms called min cut algorithms, sometimes called max flow, because they are duals of each other and they are the same, that allow you find that segmentation in a relatively not too complex a matter. fast min-cut algorithms exist. We are not going to go into those here. A problem though, if we just use min-cut for doing segmentation, is that min-cut by definition tries to pull out little segments that has as few connections as possible. So what it tends to do is to pull off many small segments, little segments, cause by definition a little segment will only connect to a small number of other nodes. So really what you should do is you should consider something a little bit smarter. In an intent, in fact, what you want to do is what's referred to as normalized cut. So here is an example of a normalized cut where the volume refers to the sum of cost of all edges that touch A. And if you consider two separate graphs, then the volume of B should be the sum of cost of all edges that touch B. So we can just find the cost of the normalized cuts here. So for the example, the normalized cuts for segmentation can be seen here. These are some of the examples, and also this is also one of the examples for segmentation as a result. Let me show you the example here. So this is the code. You can find you will find it on MathWorks, and this was implemented by Ali Raza Aswadi in 2013. So let's see what the results are. So if you can see, this is the original image, and for the k-means, if we give 8 clusters, so it clusters in 8 different colors if we use only the colors, and if we use the spatial location as well, then of course the clustering changes, the regions change. And this is the result for mean shift, and here it only clusters it returns 2 clusters only. And for the mean shift, where we also use a spatial, it returns 12 clusters. And for normalized cut, it just returns 369 normalized cut. So you can see that these segmentation algorithms do not work well when we apply it directly. We have to vary different parameters which are associated with these clustering algorithms. Like you have to vary the number of clusters for k-means, you have to vary the mean shift parameter, that is the mean shift bandwidth, you have to vary the number of cuts parameters for basically the graph cut algorithm or the graph cut algorithms. So these are the hyperparameters which needs to be tweaked when you apply it for a certain application or in your own environment. Now, which algorithm to use when? So mostly k-means algorithms are used for summarization or quantization. So they actually aim to preserve variance of original data and can easily assign new point to a cluster, like in these images. And if you want to use image segmentation, then you should prefer agglomerative clustering. So it is more flexible with distance measures and can be based on boundary prediction. It adapts better to specific data, and hierarchy can be useful in this case. So you can just stop at any hierarchy. So if you want over segmentation, if you want under segmentation, or if you want in between, so if you want to just stop in between, so you can just use a certain kind of threshold which stops the clustering process. Now, the things to remember in this video is that k-means is useful for summarization, building dictionaries of patches, and general clustering. Agglomerative clustering is useful for segmentation, general clustering, and spectral clustering is mostly useful for determining relevance, summarization, and segmentation. So if you have any questions regarding this particular clustering techniques, you can leave a comment, or you can just ask me in the live session, or you can ask me the questions at Google Classroom. So I will take a leave now. So we will in the next lecture videos, we'll mostly focus on the supervised learning, where we discuss the applications for regression and classification or categorization. Thank you.